All right, I'm posting a worked out solution to this example from the slides from October 23rd. This was from my extra slides. So in this problem, there's a person that sits on a stool. It's free to rotate. He's handed a rotating bicycle wheel, initially rotating clockwise at a particular speed. He flips the wheel over so that it's rotating at the same speed but counterclockwise, and we want to know what is the person and the stool's new angular speed. Okay, so the principle we want to use in this question is conservation of angular momentum. To help understand this, I'm going to draw it from the top. So I'm drawing the person's head here. Imagine that you're looking at this from the top, and then they are, sorry, this is a terrible drawing. Let me try again. All right, I'm just going to draw the person's head, his arms sticking out, and here's the wheel rotating. Okay, and it starts out rotating clockwise, 250 radians per second. Okay. Now, after this, he turns the wheel over and it's still rotating, but now it's rotating counterclockwise at 250 radians per second. This is basically like a recoil problem in linear momentum. So, you know, with linear momentum, if a person throws something, then they recoil away from this. In this case, there's going to be a recoil in the person's angular momentum, or we can think of it kind of like a recoil. So since the net angular momentum can't change, so our L initial is equal to our L final. So our initial L is the angular momentum of the person plus the angular momentum of the wheel. And our final L is also the angular momentum of the person plus the angular momentum of the wheel. Now, in this case, the initial angular momentum of the person is 0. So the initial angular momentum is only the angular momentum of the wheel. And then the final angular momentum still needs to be the same. Okay, so let's first find before we find that initial and final angular momentum, let's think about what we expect. So we know that the total angular momentum to start with is in the clockwise direction, which is less than 0, right? So this initial angular momentum is going to be negative. In the end, we expect then that the final angular momentum is also negative. So the wheel afterwards, in this state here, is rotating counterclockwise. That means that its angular momentum is positive. That one's greater than 0. And so to sum up to the same total angular momentum as our initial value, this angular momentum of the person must be less than 0. Okay? So we're going to expect to get a final angular momentum like this. Okay, so let's use this principle to solve the problem. So first let's find the angular momentum initial. So that is going to be I omega. In this case, we need the I of the wheel times the omega of the wheel. We know that the radius of the wheel is 0.5 meters, and the mass of the wheel is 5 kilograms. We're going to assume that the person's lost my train of thought. We're going to we know that the moment of inertia of a wheel is mr squared. We can assume that it's like a hoop. Most of the mass is on the outside. And so that's 5 kilograms times 0.5 meters squared, which is 1.25 kilogram meters squared for the moment of inertia. And we know that the omega of the wheel initially is negative 250 radians per second because it's rotating clockwise. Okay. Now, our L final of our wheel is going to be I of the wheel, which hasn't changed, times omega of the wheel final. And so that's the same 1.25 kilogram meter squared times 250 radians per second. This is our omega wheel final is now 250 radians per second. So our Li is equal to our L final. It's our Li wheel plus Li person equals L final wheel plus L final person. That's 1.25 kilogram meter squared times negative 250 radians per second is equal to 1.25 kilogram meter squared times 250 radians per second plus L final of our person. So our L final for our person is equal to 500 radians per second times 1.25 kilogram meter squared. And this is going to equal I of the person plus stool times omega of the person plus stool. And this I was given in the problem as 4.7 kilogram meter squared. So our final omega, oops, I dropped a negative sign up here. Apologies, this should be negative. So our final omega is negative 500 radians per second times 1.25 kilogram meter squared over 4.7 kilogram meter squared, which gives us negative 133 radians per second. And I will post these notes on Moodle in the October 23rd section, in the 10D section, in addition to posting this video on YouTube. Thanks.